Between 2023 and 2025, an extreme El Niño trapped massive amounts of heat across the world's oceans. This triggered the fourth global coral bleaching event. When ocean temperatures push past a coral's physical limits, the animal becomes severely stressed. To survive the immediate shock, the coral polyps expel the microscopic algae living inside their tissues. These algae are called zooxanthellae. Because they provide over 90% of the coral's food, losing them means the coral begins to starve. Without the algae, the coral's vibrant colors vanish. The living tissue turns completely transparent, revealing the stark white calcium skeleton underneath. The scale of this heat stress affected roughly 84% of the world's coral reef area. Without these healthy reefs to dissipate wave energy, billions of dollars in coastal infrastructure and local economies were suddenly exposed to unchecked storm erosion. Looking at this massive die-off, marine scientists reached a grim conclusion. The extreme temperatures appeared to guarantee a complete and inescapable loss of global coral ecosystems. But the data from the Pacific coast of Costa Rica, specifically the Gulf of Papagayo, told a different story. This chart illustrates the intensity of the heat wave using a metric called degree heating weeks. You can see the 1997 El Niño peaked at a 4.1. The 2023 event spiked to a record-breaking 10.2 degree heating weeks, more than double the previous historical maximum. Based on everything we knew from the global baseline, that specific amount of thermal stress should have wiped out every coral in the region. Yet, the destruction was highly uneven. While some spots experienced near-total mortality, specific reef networks in the Gulf remained stable and miraculously survived the peak temperatures. Curious, leaning in, if the ocean water was essentially boiling, how did these specific corals manage to avoid extinction? To understand how they survived, we have to look at the atmosphere. Not all El Niño events operate with the exact same mechanics. This map shows a canonical El Niño. Heat builds heavily in the eastern Pacific. This heat mass disrupts high-altitude pressure, causing Atlantic trade winds to weaken and stall. Without evaporative cooling, Caribbean and Florida surface temperatures skyrocket, cooking the reefs below. Now look at this alternative pattern, a Modoki El Niño. Here, the warm anomaly is trapped strictly in the central Pacific Ocean. Because the heat is positioned differently, Atlantic atmospheric winds actually strengthen. This rapid airflow causes localized cooling, sparing Atlantic reefs from heat stress. A reef's first layer of defense against a marine heat wave heavily relies on geographical luck and which specific flavor of El Niño happens to develop. But Costa Rica sits directly in the eastern Pacific. It took a direct, inescapable hit from the deadly canonical flavor, and yet communities of its dominant Passalopora corals survived. Their survival stems from a localized oceanographic feature known as seasonal upwelling. In the Gulf of Papagayo, deep, nutrient-rich water forcefully rises to the surface. This rising cold water acts like massive underwater air conditioning. It breaks up the stagnant heat, offering corals a physical reprieve from the boiling surface temperatures. This compares a standard coral polyp on the left to a Papagayo reef polyp on the right. The surviving corals possessed higher genetic diversity and harbored heat-tolerant symbiotic algae called durastinium, which acts like microscopic armor against thermal shock. Retaining these specialized algae meant the Costa Rican corals could continue to heterotrophically feed themselves, maintaining enough energy to partially recover even as the surrounding ocean warmed. The survival of these corals relies on a layered formula: the macroclimate flavor of El Niño, the regional ocean upwelling, and a microscopic genetic defense system. As global average temperatures continue to climb, extreme marine heat waves and intense El Niño events are guaranteed to become more frequent. The data forces us to accept a harsh reality. It is physically impossible to save every single coral reef on Earth from the coming heat. The new imperative for marine science is to locate and rigorously protect what are known as climate refugia, isolated pockets like the Papagayo upwelling zones where local conditions naturally buffer against global warming. Mapping these rare global refugia requires thousands of data points. Organizations like NOAA's Coral Reef Watch rely on massive amounts of crowdsourced reports from everyday divers and snorkelers to track exact ocean temperatures and bleaching locations. By documenting these anomalies of survival, local citizens provide the specific coordinates researchers need to prioritize the conservation of the world's most resilient reefs.